So, hi, we are talking about a new method to determine the added mass of two-dimensional objects in potential flow. We remember, do we have potential flow and we move an object in potential flow, we will theoretically not experience a drag because if we look on a cylinder, because the streamlines connected to the cylinder, they are symmetrical, though we cannot have a force on this object in potential flow. In a inviscid fluid. So, do we have an object that is accelerated in an inviscid fluid? Then we will experience a drag as a result of displacement of particles, fluid particles, close to the cylinder, depending on the form of the cylinder. And this drag we experience can be translated with help of that we make the model that we say we do not only accelerate the mass of the cylinder, we accelerate a kind of additional mass, which is the added mass. And this added mass is generating this additional force on the object if we accelerate the object. So as a result of object acceleration, we also accelerate particles close to the object, and we do not only have the force that is a result of the mass of the object itself, we also have to add a mass which is represented in the particles that has to be moved during this acceleration of the object. And this additional mass is called the added mass, and we can calculate the added mass theoretical with help of the potential theory. So now we will talk about another method, a new method to calculate the added mass, not using potential theory. So then we have to go to the next slide. So I will show you then how you can generate a kind of potential flow model with help of a die and a lattice you use. So you have a piece of paper and you have a lattice on this piece of paper and you have a die. And I will suggest that this die can have 4 results: north, south, west, and east. And we will choose these directions in connection with the model randomly. So that means we want to generate a kind of source with the help of a random walk. And what is the problem with a source model we generate? And what is the background of the potential flow theory? I have sketched a kind of source model. I have particles together, and I add a particle in the middle. And if I want to calculate the movement of all other particles, then I have to remember that all particles have an influence of each other, and also boundaries have a particle have the influence of these particles. Close particles to the center, they have to move a long way, and far away particles, they have to move a little bit. Yes, and that I want to model. Usually we model this with source Scienc models in potential theory, and we are adding the velocity vectors, vectorial. Yeah. So now we want to make a new model, and this new model is a random walk model, and we have to show that this random walk model gives results that have a connection to the displacement of particles. And I want to show you especially that I can use this model then to define the added mass of two-dimensional objects. And I will show in 2 examples that it works. So now we see this source model and one red particle is coming out of the source and is displacing all these blue particles then. So what is this random walk source model? I will suggest that you need a lattice and a die. Yeah, you go to the next slide. Yeah. You have to imagine that a particle in the center is coming out of this source, and then you have all these blue particles around then. Yeah, and in this random walk model, you cast the die and you test an environment. You say, let's go to the north, and then you go to the north, and then you experience there's a particle. I cannot be there. So I step on this particle and I use the die again, and I say now to the east, and then they see, oh, there's a particle, and I cast the die again, and they say to the north, and I come to this position, there's a particle. Okay, I cannot be there. I step on this head of this particle, and I use the die again, and I go to this position, and then I find there's no particle, and I can settle down there. And the next particle is coming out of the field, is in a random walk experiencing the field and the surrounding, and settles down where it can settle down, where they have no particle. And you make this additional, then you have kind of started a kind of source there. Yeah? Particle coming out, checking the environment in a random walk, finding its place and settle down. So now let us describe this model and show that this model has a kind of gives result in the connection with potential flow. So we have also our piece of paper with its separated in a lattice with cells that have equal uh, um, equal separation then, yeah, and we are modeling a fluid flow in the presence of obstacles. Yeah, so we say each cell has a name. The name is Aij. Yeah, that's showing the position of the cell in the lattice then. Yeah, and then we have three um, values these cells can have. One means this cell has one particle. Yeah, I've chosen one. Yeah, we could have also chosen a color or other things. Yeah, then 0 in a cell means this cell has no particle, and 2 means this cell cannot take a particle and cannot become occupied. Yeah. So, and we make this random walk in this cell environment. So I go to the next slide here. So on the right side, I have sketched the kind of dice, yeah, 4 directions, north, south, west, and east, which will be chosen randomly. And on the left side, I have shown this lattice there, yeah, and this orthogonal lattice is here shown that we have a separation line. I don't know, we have a kind of start line or a line that stops particle from going down, yeah, in this direction. So they are all occupied with 2. That means uh, this cell cannot be occupied. Yeah, and then we have some results of a random walk. We have here this uh, cells which are occupied with particles, 1, 1, 1. And we have all these cells that have no particle. And we imagine we have the start line, yeah, and randomly we choose a start position. Let's choose this start position, and we use the die then, and we rotate and we say north, and we go up to north. And if we go to south north, then we experience there's a particle in cell north, so sit on the cell now and cast the die again. And we cast the die again, and then we get this result, go to the east. And you go to the east, and in the east we experience, in this position, there's a particle, you cannot be there. Yeah, and we cast the die again, and then say south. But if you try to go to the south, then this cell says, I have value 2, you cannot come to me, to go back and try again. And we cast the die again and then said north. So you come in this position. And the next, and then it's occupied. And the next is west. This is occupied. You cannot occupy it. And then the next is north. And now, if you then experience there's no particle in this position, we can settle down in this position. And then the particle has found its position. Yeah. So means particle coming out of a source, here a source line, exploring the field in 4 directions, experience other particles sitting there, sitting on the top of it, and try the next position till they have found a position that they can settle down. Now we have to show that this model we use here is a displacement model that works in connection with fluids, which displace or fluid particles or other particles that displace is other. Yeah. So here we see a start line. Let me see. I have the mouse there. So we see a start line there, which has a special angle. Yeah. Then here on the values of this start cells is 2. Perhaps you cannot see it, but the value is 2. Then we have a wing section. That's the coarse definition of a wing section. It goes from here to here, and here we have a separation line. This separation line is normal to the start line of the particle coming out of a line source. And here we see particle that has come out of the line source, generating kind of cloud, and this cloud of particles is now moving towards the wing section. And we have to look on the fronts that we experience when this particle cloud is moving towards the wing section. And here we see results of such a model, a random walk source model, start line, and we have a cloud of growing particle growing in direction of a wing section, and here we have the separation line. Yes, now we have some time steps later. Now the fronts have found the profile. They cannot go through the boundary of the profile, and we get 2 separated fronts. And here the upper front has reached the rear edge of the profile, and the lower front is lit forward in the direction of the separation line. And I have showed in the paper 1997 that the difference between the particle here in this position and this position is related to the lift coefficient. So that means we have generated a displacement model with help of a random walk algorithm we have defined, which is the random walk source model, and we can use the random walk source model to generate fronts moving towards objects, and here it's a wing section, and we get physical results we can use out of this displacement model, and that shows that displacement model works because we can define the lift coefficient of this element only as a result of the geometrical displacement of particles then. So now we want to talk about the added mass, because if you have a displacement model which shows us how particles displace each other in the plane with the help of the random walk, how can we use this displacement model to define the added mass of an object, two-dimensional object? And then we go back to Rieke, 1888. Here we see a picture where we have moved a cylinder from the left side to the right side. We see only part of the cylinder here. That has moved from the left side to the right side. And Rieke, he showed in 1888 in potential flow and in viscid fluids that if you have an object moving from the left to the right and you look on the particles which are displaced by this object, then this particle will make a loop and will settle down in a new position from here to here. Another particle which was first here is moving this loop during the movement of this cylinder there. And that's the third part. That's the movement as a result of the movement, and the movement is with constant velocity. So that was Rieke 1881, the German, I don't know, physicist, mathematician. Yeah. So Sir Charles Darwin, he showed in 1952 that the particles which are here in this position and between this position and all these positions here, that these particles are exactly the added mass of a cylinder and will generate a drag if the cylinder is accelerated. That was the result of the uh, scientific work of Sir Charles Darwin. He said, all these particles behind this, between these positions, they are the added mass. And now we want to find a connection to the random walk source model. Here we have a plate which has a length 2a, so little a, AST, so 20 pixel, can we say, to is displayed here. And then on the left side, we have a start line where particles coming out of a line source, and these particles are moving in a straight front towards this flat plate. And here, when the particles have reached the plate, then we see that the fronts are separated into upper front and lower front, which are deformed. And if you see on the deformation of the front, when the two fronts meet again, that must be here. Then we have a deformation of this front, and we have an area which has no particles in it. So when these two fronts meet, and we say the area of this missing the area of missing particles times two multiplied with 2, that will be the added mass of this flat plate. That one we try to test out. So we say we have fronts moving in the random walk model towards the plate here, and we have deformation of the fronts, and with this two fronts meeting in the rear position of the plate, then the area where we have no particles is 50% of the added mass. So if you want to test that, we have to go to the laptop, so it's possible to go to the next slide. So here we want to show that our idea that the area of missing particle time multiplied with 2 is that added mass should be shown in this diagram. So here we have relative added mass to area versus theory. So that means here I have the area of the environment where we have no particles, multiplied with 2 is here, divided by the theoretical result, how we define the added mass of a flat plate, which is pi times a squared times density, but density is 1, so we haven't written it down. And if these two values, if they together give 1, then we know that we have found the added mass there. And we see, if you here you see the time steps of this particle coming out of the line source, and we are approaching the profile closer and closer. We come to the profile. The fronts are separated of the plate then, and then the two elements, the two fronts are coming together. When they come together, then the area of missing particle is the same area that defines the added mass. Then this here. Yeah, and we can also show it in a next place with the other diamond shape form. The usual added mass of a diamond shape form is we see it in the next slide, 0.76 times pi times a squared. And here this blue line shows when we are looking on the area where particles are missing. This area multiplied with 2 should be the added mass, and we look in the diagram that comes here. So we have these fronts approaching this diamond shape, coming to the diamond shape, passing the diamond shape, and when they meet again on the rear point, then the factor 2 times area divided by the theoretical definition of the added mass is again 1. So we have also talked about a displacement model, which is very simple, which is a random walk model, which can define for us properties of potential flow. One property I showed very short was that you can define the lift coefficient of wing section with help of this random walk source model. Yeah. When here I showed that you also could use this displacement model to define the added mass of two-dimensional objects, and we can imagine that would be the same way, straightforward, to define the added mass of three-dimensional objects with this random walk source model. Thank you very much for your kind attention, and now you can ask questions.